can say that because preaching to the choir here. Let me say again an announcement I just made. It was a reminder of this class of 15, 5 people, 1/3 of the class has turned in the research papers, and we're rapidly running out of term for that. The first test, I still have 3 people who haven't turned in the first test, and I have 6 people who haven't turned in the second test. And you will be getting the third test this week, I believe it will be. Okay? So, any questions on anything we've done up to now? Math-wise or otherwise? Okay, we're in section 3.8, Newton's method. Next to the last section in chapter 3. So, and this is a very short section. Don't think it'll take us long to get through it. And then we'll do differentials, which is a little bit longer section, but not super long. So we might make I think we'll make great progress on that one today too. And hopefully I have ready for you on Wednesday, knock on wood, the test for chapter 3. I was saying to the 2 folks who were here earlier, while I was a little late coming in today, I was on the phone with the dean trying to track down some information she said she was going to send me that I couldn't find, and then she told me she had forgotten to send it. So we were trying to deal with some stuff. And I said, hey, look, I've got class. And finally I got her off the phone. But we're desperately working to try to complete fall schedule. Because 2 huge changes are happening in the fall. Number 1, redoing everything we do with developmental. Okay? So that is a huge, huge part of our classes and scheduling and stuff like that. So that's taking place. And they're changing all the times for fall. We're going to be starting classes at 8:30 rather than 8. So I guess Jeff State did it and everybody loved it. Loved the idea, so that's what we're planning to do here. So that changes lots of things. So doing fall schedule was never easy, but it's now far worse than it ever was before, this time anyway. Okay, so I will be tied up with that too, so come see me if you need me, but if I'm wacko, that's why. Okay, any questions before we get started? All right, we started talking about Newton's method and, showed that, if you use the first derivative from what you're doing is looking for the zeros of a function. Pick a point you think is fairly close to a 0. Figure out what the value of the function is at that point. It's usually not going to be 0, but it's hopefully going to be not too far away. Take the derivative at that point, and that points you closer to the 0. Okay? So keep doing that every estimate that you do. So here's the method. For approximating 0 as a function, let's pick, let alpha c equal 0. Okay? We don't know where c is. But let alpha c equal 0. That's going to be a 0 of the function we're looking for. Where alpha is a differentiable on some open interval that contains c, and then to approximate the value of c, here are the steps. Make an initial estimate. Choose an x1 somewhere close to c, okay? Hopefully it's in the open interval where the function is differentiable. If it's not, you can hang this up, okay? Get it, some value close to c. We don't know what c is, but some estimate that you think will be fairly close to c. That's your F1. Okay? Now, they don't do a really great job of expressing this as a method. I'll fill in the gaps here. Once you make an estimate of x1, then figure out what f of x1 is. Okay? Then take a derivative at x1 and figure out what f prime of x1 is. Okay? Because remember, f is differentiable on that open interval that contains c. Okay? Now, your next estimate, your first estimate was x1. your next one is going to be, this will be x2, will be x1 minus f of x1 divided by L prime of x1. Okay, what you just calculated, the ratio there, and that's going to give you x2. Then turn right around and do the same thing again. Take the derivative. You've already taken the derivative. You know what the function is. You know what the derivative is. Plug in x2, and that gives you the new estimate for x3. x3 would be x2 minus the ratio of alpha of x2 divided by L prime of x2. Okay? And keep going. X to the n plus 1 will be xn minus f of xn divided by L prime of xn. And when you get the last two estimates that you have within your desired accuracy, you decide ahead of time, how close do I want this to be? Okay? 1/10, 1,000th, 1/10,000th, whatever you want to choose. And you say, if I get within that close, I'm going to be satisfied that's close enough to see. Okay? So you determine that probably a priori, ahead of time. And then every time you do it, you come up with a new x, compare it to the old x. If it's within the desired accuracy, stop. Use the newest x you have. If it's not within, do it again. You'll be surprised at how quickly Newton's method converges on the answer, or something close enough to the answer. Okay? And guess what? It doesn't matter which order you put these. They say xn minus xn minus plus 1. You're doing absolute value. It doesn't matter which one you put first. So just, whichever one. Otherwise, return to step 2 and do it again and again until you get within the your desired precision or accuracy. Each successive application of this procedure is called an iteration. It's an iterative process, and it converges pretty quickly. Now, they have a little blurb here off to the side that I had never heard before. Isaac Newton, brilliant character that he was notorious for coming up with stuff, and he did not want anyone questioning. So he tested and made sure it was absolutely right before he would publish it. Unlike Gottfried Leibniz, who published as soon as it popped into his head, and then found out, whoops, that's wrong, and had to go back and undo it. Newton could not stand that, so that's one reason Leibniz published calculus before Newton did, because Newton wanted to make sure it was right. Well, he came up with this method and actually wrote the book in 1671, but would not allow it to be published until he was certain everything was correct. So it didn't get published until 1736. Look at that. That is 5 years. Okay. Goodness gracious. He was dead by then, wasn't he? Okay. But in 1690, 19 years after he had written his book, Joseph Raphson, who was dead before the other one was published a paper describing the method for approximating the real zeros of a function that was very similar to Newton's, and for this reason, it's often referred to as the Newton-Raphson method. I'd never heard that until I read this little blurb. So there's another potential paper topic. Who in the world is this Raphson guy? How did he come up with this? How did it differ from Newton's? If it differed any, that's interesting. Okay. So, any questions on Newton's method? Let's do Newton's method. It said calculate 3 iterations of Newton's method to approximate a zero of f of x equal x squared minus 2, and use x equal 1 as the initial guess. So they're telling you everything. So before we do anything else, what had we better do with f of x? Oh, that sounds like a great idea. Clever of you to think of it. Okay? Let's take a derivative. Let me get my pen set up. It won't set up. There we go. F prime of x is equal to what?
2x.
2x. Okay, now what do we do with that? Okay, we've already they told us what x to use. Okay, x1 equal 1, right? Okay, what's another thing we better calculate before we get started?
What f of x is?
Yes, what f of x1 is. So go back to what f of x is, x squared minus 2, plug in 1 there, and what do you get?
Negative 1.
-1. And we ought to calculate what? F prime of x1 is. And f prime of, when x1 is 1, what is that equal to? 2. Okay? So, we know our x1, we know our f of x1, we know our f prime of x1. What's our x2? x1 minus, what's Newton's method tell us?
X1 minus, that would be negative 1 over 2.
Yes, exactly. Well, it's x1 minus that, so x1 is 1 minus a minus, so that's going to be plus, right? 1/2. So our x2 would be 1.5. You see it? Make sense? Okay. Now, do you prefer 3/2 or 1.5? I really don't care too much. And here's Tyler.
1.5.
Okay. Thought I found you, and now there you are. Okay. All right. We have every other student on the roll for a while there, the 5 that are here. Okay. You prefer 1.5? Okay. So we have our x2 is 1.5. We need to do f of x2, which would be, you wanted it, so you got it. That's 2.25 minus 2. 0.25, and f prime of x2 will be
4.5.
Second?
4.5. Right?
Say that one more time.
Oh no, it'd be 3.
3, right. Agreed? 3. Okay. So our x3 then would be x2, which is 1.5 minus, you want to stay with decimals or do you want to go to fractions? Okay. Either way, well, actually, using a calculator, decimals will be better. That would be 0.25 over 3. Now, there's a minus sign this time. So what does that give us?
17 over 12.
Say again?
It's 17 over 12, or 1.416666.
1.416 with a bar over it. Okay? Now, have any of you stopped to think what the real answer is? If you're looking for f of x is x squared minus 2 and you want to know what the 0 for that is, what would that be? What square?
The square root.
Square root of 2, exactly. Square root of 2 is 1.414. Look at this. We went from 1 to 1.5 to 1.41. We're already within 3 digits of having the answer. Okay, in just 2 steps so far. So what do we do next? There's our x3. Now, I would leave that in the calculator with all those digits behind it, okay? And let's do what, in fact, you may even want to save that, okay? And so the x3 is 1.416 with all those sixes in a row. F of x3 is going to be square that and subtract 2 from it. What do you get? All those digits there, just square it and subtract 2.
6.9.
Say again?
It's 6.
Ooh. Okay. Awfully close to 2, a little bit more than 2. So it's minus 2 is going to be a pretty small number.
1/144.
1/144. You went back to decimals, didn't you?
Well, I mean, it's 0.006.
0.0065. 69.
And then 4 with a bar over it.
4 with a bar over it. Okay? Now, what that is telling you, that with this as a 0, we're already within 3 decimal places of being a real 0. Okay? You're awfully close to 0 there. Okay? And let's go on and do what F prime of x3 is. There's our x3, 1.4. Okay? So that's double that. Okay? Well, double that would be 2.82 3333333. Huh?
With the 17/12, I got 2.83 with a bar over it.
3 with a bar over it. Okay? So, all right. So now our x4, I'm not sure we were supposed to do the x4. It said calculate 3 iterations. This is our third calculation. I think it's right. x4 is equal to 1.416 with a bar over it minus 0.006564 with a bar over it over 2.83 with a bar over it. Is that what I understood you to say? Or is it?
It should have been 0.00694 with a bar over it.
Oh, 6. Okay, I'm sorry. Say that one more time.
0.00694.
Okay, sorry. Okay. All right. I thought that seemed like a weird number. 694 with the bar over it, and this is 694 with the bar over it. Okay? It's like living in the basement with a bar over it. No, right. Okay. If you do that, you're going to see it's a pretty small, because you know already this one's a little bit greater than the square root of 2. And you're going to subtract a very small number from that to get you even closer. And what would that be? And here I would be using your stored things a lot, but whatever. What do you get?
0.91.
Well, the x4 should not be that. Oh, you're just doing the fraction. Is that right? The ratio? What we do is 1.416, whatever that last one was, minus that. So yeah. So what does that give you?
0.91. And then 5 6s.
Okay. That's what this ratio is here? There's something wrong with that picture, I think. Go back here. 1.416666662 minus 0.0069444444, as many as you got there, divided by 2.8333333333, Yeah, it's going to be something far closer to this, or something like that. Because that's an incredibly small number right there.
Yeah, now that time I did, I got 1.413547703.
Oh, okay, well, we'll stop right there. Well, what we know square root of 2 is, to 4 digits, is 1.414. That's already there to 4 digits. Okay? How precise do you want it? You're never going to get the square root of 2 because that's an irrational number, but you're going to get closer and closer and closer and closer and closer to it. So that's close enough for me. They said do 3 steps. That's what we got. Let's see what they did. Uh-oh. Seems like we may have made a little, well, they could have had round off error here. Okay? Let's see what the first one said. The first was 1 minus, and your f of 1 was minus 1, f prime of 1 was 2, so your ratio, they gave you that, and then the f, yeah, so you got 1.5, we got that. So then we had a 0.25, which we got, there it is, and that was just a 3, we got that, and that gave you 0.8333, we got that. I remember somewhere there, there it is. So your 1.416, we got that one, minus 0.06945, it must not have been, we did a round off there, it looks like, or they did one. And your f prime was 2.83333, and then they rounded up to 4. So I think they made an error, go round off thing there. And that gave us 0.2 of that. Well, yeah, we didn't do that. 1.414. Okay. So they came out a little closer than we did. I think either we or they had a little bit of a round off error somewhere in there.
Well, and on this one, I didn't use the 66666.
Oh.
I just
did 7.
16.
Oh, 16. Okay, yeah. It should have gone with 7 anyway. Yeah. Okay. Okay, so yeah, we were awfully close in very short time. Okay? So, let's see what they did. All right. We had some round off error, which is understandable. We had to stop somewhere. So because of that, we did exactly what they did, f of x, f prime of x, and then here's our formula, okay, and those are results. It's got down to that third answer before we got a little bit of deviation from what theirs was, so we were awfully close. We're still good within 4 digits, just like they were. Okay, of course, in this case, you know that the 2 zeros of the function are plus or minus square root of 2, and we had chosen plus 1 as our first, so we were heading toward that one. So 1.41414, and notice what they got, 41416. Okay, so there they are within 2, that's tenths, hundredths, thousand, 2 millionths, okay, of the answer. Pretty close, okay? So after only 3 iterations of the Newton method, you have attained an approximation that is within 0.000, that's 2 millionths of the actual root. It's close enough for me, okay? I'll live with it, okay? After a while, your calculator isn't much more precise than that, so yeah. So the first iteration process, as we saw, here's what we did. Here was a function x squared minus 2, okay? We chose as the first 0 x equal 1, knowing that wasn't true. There's your f of 1 at -1, and f prime of 1 at 1.5, okay? No, I'm sorry, f prime of 1, whatever that was, and then your first derivative aimed you right over there, so your x2 was 1.5. You overshot it. Well, then you went to up here and got what 1.5 was, and then the derivative there, and you're going to come in between this one and that. Okay, between that and the real 0, which is a very close approximation. Chasten's here. We're still every other, no, I'm sorry. Angel skipped one. There's 2 in between. But awfully close to every other student. Okay? All right. So when, as in example 1, the approximations approach a limit, the sequence of the approximations are said to converge. I've already used that word. I didn't know they were going to use it now. Moreover, when the limit is C, it can be shown that C must be the 0 of F. Okay? Now, where do you have problems with Newton's method? It does not always yield a convergent sequence, especially if you have a horizontal tangent line. Because that's not going to ever point toward the answer. Okay? So you can't use a horizontal tangent line. So if you have a 0, you know it's somewhere down here, you're wanting to approximate it, have a horizontal tangent line anywhere close to it, you've got to get between the horizontal tangent line, which remember is our test point, critical point. So always get between the critical point and where you think the 0 is going to be. One way it can fail is shown here. Okay? Because it can't possibly, well, then if you think about it, what does the rule say? X of 1 minus F of 1 divided by F prime of 1. You can't divide by 0 to avoid those horizontal tangent lines, which are going to be at some of your critical values. So avoid a critical value. Get between the critical value and the 0, and you'll be safe. Okay? Because Newton's method involves division by F prime, it's clear that the method will fail when the derivative is 0 for any x in the sequence. So when you encounter this problem, usually overcome it by choosing a different value of x1. Choose something between your critical point and your 0. Another way the Newton method can fail is shown in the next example, and unfortunately we're going to do that, aren't we? Okay? Oh, no we're not. They skipped example 2. So let's go back and do example 2. Okay? And you can go to larssoncalculus.com for an interactive version of this type of example. Use Newton's method to approximate the zeros of f of x is equal to 2x cubed plus x squared minus x plus 1. Okay? Continue the iterations until 2 consecutive approximations differ by less than 0.001. So you want your error to be less than 0.0001. Okay? Now, it better be the first thing you do. Take a derivative. Good answer. Okay? And what is that derivative? 6x squared plus 2x minus 1. Okay? Now, you know what I want to do? I want to see where that's equal to 0, because I want to avoid that. You know? I think to get where it's equal to 0, you're going to have to do quadratic formula and come up with an estimate of that. Okay? And a 0 for that function and here's the crazy part. If you use a graphing calculator to show you where the 0 is to pick a first point, all you have to do is a couple steps. It'll tell you exactly what the 0 is. So it's a little artificial here, okay? Because if you knew that. But let's see. When x is equal to 0, this is at minus 1, right? Oh, wait, I'm sorry. X equals 0, this is at plus 1. When x equals 1, this is 2 plus 1 is 3. 4 minus 1, so that's going to be 3. So it looks like we're getting further away. Let's do a minus 1. This will be a minus 2 minus 2 and minus 2 plus 1 plus 1 plus 1, that's plus 3. So it's plus 1 also at x equal minus 1, if I did that right. So I'm going to say, let's just make a guess, negative 0.5. Does that seem like something reasonable to you? I don't know if it is or not. I'm looking for a 0 for this. So I use the easiest thing to evaluate, and that's x equals 0. That's going to be 1. Okay? So x equals 0, that's 1. Next easiest to evaluate is x equals 1. And that would be 2 plus 1 is 3. And then minus 1 plus 1 is 0. So it's 3. So when I'm going up, I seem to be getting further from my 0. So I want to go to the other way. X equals minus 1. I'll put a minus 1 in here. This becomes a minus 2 plus 1. That will be a minus 1 plus 1. That gets me back to 0 plus 1. Oh! So x equals 0, it's plus 1. X equals negative 1, it's a plus 1. If there's going to be a 0 in there, let's guess 0.5, negative 0.5. I don't know if there is, but if there is going to be one, that would seem to make sense. Okay? Now, let's just look at negative 0.1, if that's, or 0.5, if that's going to give you 0 here. I think not. Okay? Because negative 0.5 squared would be positive 0.25. So this would be 3/4 positive. That would be a negative 1 minus 1. So it's certainly not 0. So I think we're going to be okay with that. So let's use as our first value x1 equal negative 0.5. Okay? Then our x, okay. And what we have to do is f of x1 is going to be what? I think I already did it. No, I didn't. Well, I came close. But plug that in. That's
3. Oh, x1 was...
Yeah, it's negative 0.5. So that would be negative 1/8. So it's negative 1/4. Plus 1/4 would be 0. Plus 0.5 plus 1. I think it's going to be 1.5. Do it on your calculator. See, so Monday morning, the old gray cells don't do too well. Which is not encouraging, because I was hoping that was going to be closer to 0 than that. Negative 2/8, which is negative 1/4, plus 1/4, plus 0.5, plus 1. That looks like a 1.5 to me. Is that what you got? Yeah.
And the book that started with negative 1.2.
Negative 1.2. Probably a better choice than mine. Okay. And look at that. Because you can see the graph, you can see why it's a better choice. But so my thinking was wrong. I thought because the 0 was, it was going to be 1. At minus 1, it was going to be 1. In between there was going to be better. It wasn't. This will not lead you. If you look at the graph, this is going to take you somewhere to the right of that. It's never going to approach there. So yeah, actually negative 0.1 would be a better choice. I mean, an okay choice. They started with negative. So yeah, they used the graph, which is fine. You should, but if you're going to use the graph, you should be able to And probably what I should have done, now that I think about it, was chosen another f, like -2, and then plug that in. But I already knew that was going to be a really big negative number, but you're guaranteed that you're in between those two then. You weren't guaranteed that otherwise. I was just making an assumption you might dip down, you didn't. So, yeah, you should really go. So they chose, and let's back off and do it. I was trying not to look at a graph to give you a better idea of what you can do without it. So let's clear all this mess out of the way. Everything we've done is correct so far, except the choice of x1. Whoa! I erased the wrong thing. All right. All right. So say x of 1 is -1.2. Okay. So in here you use your calculator. X of 2 would then be -1.2 minus, oh, you have to do this too, f of x1 would be, and you have to plug it in, 2, you already done it, what f of x2?
5.24.
5.24, wow, big number. Elijah's here. There you go. All right, we finally have 3 in a row now, and skipping one in between. That seems a bit large. Would you go back and check that for me, please? Be sure you put -1.2. What you get?
5.24.
Wow. Okay. Let's step through it and make sure. Maybe I'm thinking poorly. Okay. 2 times a -1.2 cubed is going to be a slightly negative number, right? Well, a fairly negative number, right? Plus 1.2 squared, and that's going to be positive because of that, right? Okay. Plus 1.2, because minus and minus is plus 1. That first one is going to be fairly negative, right? And then you're adding to it. I don't see how you can get it to 5. Maybe not. Okay.
We're using the first derivative.
Okay, yeah. No, we're doing the f.
Oh, no, that one was...
I'm sorry.
Yeah.
What's f of x1? F of -1.2.
Is 0.184.
I'll buy that. 184. Okay. And f prime, you were giving me f prime. I was, okay. All right. And that was, I can buy that one. That's what you say, 5.24. Okay. Now, Jeremy's here. All right. Getting a good crowd today after a while. Okay. Now we got 5 in a row. We didn't have any in a row before Elijah came in. Okay. So that's -1.2 minus a 0.184 over 5.24. And you see that's going to be a pretty small number. And what do you get that to be?
-1.2351.
2351. Okay. Now, that would be x of 2. Okay. They use one more digit. Okay, now, what we have to do here is now do f of x2, which is take that number and put an extra 1 after it because they did in the book. Okay. And do f of that, which is 2 times that thing cubed plus that thing squared minus that thing plus 1. should be even closer to 0.
Is negative 0.0007.
Wow. Okay. Okay. Now they got 00771. They only had 2 zeros. 771. Now, maybe what you're doing is actually faster than theirs is, but yeah. If so, I mean, I'm happy with it. But okay. And then let's do our f prime at x2, and that's probably going to be a pretty good sized number. And again, it could be just round off differences. And it can happen that rounding off one way is going to get you closer than the way they rounded off.
Maybe getting confused on this, but this is what I'm getting. I thought that was 3 zeros. But it could have been 2.
It's point. Yeah. See, yeah. The first minus moves it one place and then 2 more. So it's 0.00.
Oh,
yeah.
So have I at 3 zeros?
Yeah. Okay. 007. Woo! Get out of there. Yuck! This isn't working. There, finally. Okay. 007 something another. And they got 771. So I'll just go with them on this because you got something pretty close to it. F prime of that negative 1.2351, they did 511. They got that to be 5.68276.
5.6826.
Okay, they got 76. Okay. Now, our x3 then will be our x2, which is negative 1.23511, minus, now, you got a minus and a plus, so that's going to be a plus 0.00771 divided by 5.68276. I think that's what they got. And anyway, you do that, and you haven't changed much at all. So, I mean, why do they keep going? They said get it within 0.0001. Well, you see their x3 and their x4. Yeah, you're closer than that. You have zoomed right in there. This is going to be the x4, according to what they get, is negative 1.23375. Okay, so the difference between these two is not there yet, but the next time you get the same thing. You get the same answer as you got last time. So stop. Okay. That's going to be close enough. Negative 1.23375 is what they say it is. Two successive approximations differ by less than 0.0001. Estimate that to be your answer. You're going to be good enough. Okay? Now, your calculator knows how close you can get. No, I didn't say that right. It has internally set a much more stringent 0, but it does all the calculations really fast. And when it gets within whatever, and believe it or not, your calculator, how many digits can you show in your calculator? Just
9 or 10.
9 or 10. Your calculator is going to round because it's going to keep things more than that. It's probably going to go up to about 12. And then after that, it's not going to do any more because it can't show any more than 9 or 10. So it's going to have your error to be less than, say, 10 to the minus 12. And once it gets there, it's going to stop. You're never getting an exact answer on that. You're getting a round off, but it's within the digits shown on your calculator. But even the calculator isn't precise. Now, if you did try to keep going, just out of stubbornness, after a while, you start introducing errors because your calculator can't round it so much, and it's going to round, and then your rounded answer is going to be worse than your previous answer. Okay? And then it's going to start getting haywire. So after a while, when you get within whatever you've determined is going to be your precision that you're happy with, stop. Okay? You can keep going and start getting some wrong answers. Don't do it. Okay? Now, example 3, okay, is going to be the example that proves another place where Newton's method fails. So that's what we're going to now, is example 3. Here it is. Ha! The function f of x is equal to x to the 1/3 is not differentiable when x is equal to 0. Well, what is your f prime? 1/3 x to the negative 2/3. And obviously you can't put, that's 1, and that's the same as 1/3 times the cube root of x squared. Okay, that's what that means, right? And you can't plug in an x equals 0, can you? Because then this will be 0, the cube root of 0 is 0, 3 times 0 is 0, 1/0. You can't do it, ever! Okay? So therefore, that function is not differentiable at x equals 0. So it says, show that Newton's method fails to converge using x equal to 0.1. Okay? That's not 0. Okay? But guess what? If you were to draw that function, the cube root of x, okay, isn't it going to look something like this? Let's see if I can. Okay, it's only 0 is at 0, okay? And if you start looking for it using a derivative that can't be 0, it's not going to do. So it says show that. So you see at 0.1, you're going to start here. It's going to point you back, and it's probably going to get you on the other side, and then you just start crisscrossing and probably getting further and further away. Let's see if that's what happens. So our x1 is, yuck. I've already done your f prime, okay? So when x1 is equal to 0.1, f of x1 is going to be what? The cube root of 0.1. Anyone do it? Cube root of 0.1.
So for f of x, I got 0.464.
0.464. Okay, cube root of 0.1. Yeah, okay, we'll buy that. And f prime of x1.
1.5471.
Okay, so our x2 is going to be x1, 0.1, minus f of x1, 0.464, divided by 1.5471. Okay, see what that gives you.
That gives us negative 1.999, and it's like, it's like 2 times.
Okay.
1.1999.
Or 1.199. Sounds a little better.
Oh, sorry, negative 0.199.
Oh, okay, got it. I was going to say that, yeah, that, I didn't see how it could get that big. Okay. Negative
0.1999.
Okay. All right. Okay, almost negative 0.2. Okay? Now, what you've just done is crossed over a place that doesn't exist. Okay? If you use that for your next x3 and then plug in, what you're going to get is further on that side, and then further on this side, and then further on that side. You're going to get further and further away. Let's try it and see. Or do you want to just use the book?
I mean, would it mess up if you rounded up?
What's that?
I said,
Okay. To keep us from taking so much class time doing it, let's just go straight to their table. Okay? And there's your F prime, just like we got it. And that's what we have. Ha! I didn't think of this. I was just plugging in values. They actually found out what this is. If you look at this, this is, there's your x to the 1/3, and there's your x to the minus 2/3, and the 1/1/3 is going to flip this up and make a 3, and this is going, dividing by the negative, flips it up, and you just get this. X to the n times minus 3 times x to the n, which would be x to the n times 1 minus 3, which would be negative 2x to the n. Okay? Not very encouraging, is it? Because your first choice was 0.1, the next one is going to be negative 0.2, which is what we got awfully close to, right? Okay? And the next one is going to be positive again, okay? And basically you're ping-ponging, getting further and further away from your zero. Okay? Guaranteed. Okay? So let's do one more step. Negative 2x to the n. So you do that, and you see the first one's going to be 0.1, negative 0.2, plug in negative 0.2 here, do the same thing, you get positive 0.4, plug in that, you get negative 0.8, plug in that, you get positive, every time. This is going to be negative 0.2 times the previous one. You're getting further and further away, okay? And the ping-ponging further and further, you're not going to converge on anything there at all. They just keep getting bigger and further away from zero. You know the zero is going to be at zero. But at the zero, you have an undefined derivative. And you can't divide by an undefined number ever. So you don't want You don't want to be near a horizontal tangent line. You don't want to be near a vertical tangent line. Either one of them. Both of those are going to be bad situations to have. Okay. And you see, here's what's happening there. No matter how close you choose, there's your zero. You know the zero's there. Why were we looking for it? Well, use the point 1. Well, the function value's here, the derivative is here. But that's further away than this was. So you go down here, derivative takes you out here, it takes you up here. Derivative takes you back here, it takes you down here, there, there, there. You're getting further and further away no matter what you do. Avoid, you can't do it anywhere near a horizontal tangent line or a vertical tangent line. In fact, any of your critical values, okay? And you can't get close enough to it. If your zero is a critical value, zero, the function, is a critical value, it's not going to work for you, okay? It just can't. So Newton's method fails to converge for every x value other than the actual zero. And then it's already there. It can be shown that a condition sufficient to produce a convergence for Newton's method to a zero of f is that the absolute value of f times f double prime divided by f prime squared has to be less than 1. Okay? That's your condition for conversion on an open interval containing the zero. Okay? And you see your f double prime was not going to be defined at 0. The f prime is not defined at 0. The f is defined at 0. In fact, that's where the 0 is. But then these things go absolutely crazy outside of that. So, yeah. That's going to be your necessary condition. Not sufficient condition to produce a convergence. Okay? Now, I'm hoping they don't ask us to prove that. Okay? All right. So if you go back to that first one we did, let's see, do they do this? I don't think they do. No. Let's do the first one. The f of x is equal to x squared minus 2, wasn't it? Yeah. F prime of x we got was 2x, remember? And f double prime of x was then what? 2. Okay? Now, your condition here, absolute value of f of x, which is 2x, times f double prime of x, which is times 2, so that would make it 4x, over f prime squared. I said that wrong, didn't I? Sorry. Let me back off. F of x, I put f prime of x. F of x is x squared minus 2 times 2, okay, divided by 2x squared. Oops, that's absolute value. Okay, so this will be 2x squared minus 4 divided by 4x squared. Okay. Now, what you got to do is make sure you choose an x that'll make that less than 1. Okay? And what do we choose for that first one? I think we chose 1. So if you put a 1 in there, this will give you 2 minus 4 is negative 2 over 4 is 1/2. Less than 1. Perfect. Perfectly fine. Okay?
So why does all that have to be?
What's that?
Why does all that have to be less than 1?
Because otherwise your derivatives are going to be heading in the opposite directions. They're not going back to a zero. Yeah.
What section is this?
I'm sorry?
What section is this?
This is 3.8. 3.8. Okay. Now there's a couple people listed here. Niels, I don't know how you say it, Henrik Abel, lived in the early 1800s, unfortunately a very short time in the early 1800s. He only lived to be 27 years old. And Évariste Galois, who was younger than he was and didn't live much longer. In fact, he only lived to be 21. Although the lives of both Abel and Galois were brief, their work in the fields of analysis and abstract algebra was very far-reaching. Just imagine if these guys would have lived through the prime of their life, you know. They were barely out of their teens when they died, okay? And one died at 27, the other died at 21, okay? Now, Galois, I think his was so stupid, I think he died in a duel fighting over a woman or something like that. So, such a waste. I don't know anything about Abel. I don't remember him, any stories on him at all. Okay. Okay, on the second one we did, let's see. You have learned several techniques for finding zeros of functions. The zeros of some functions, such as this one. Remember, we did that one, didn't we? No, we didn't. It wasn't a minus, it was a plus. Can be found by simple algebraic techniques. Alpha of x equals that. Zeros of the function. Factor by grouping. Group these two and those two. I think you're going to come up with your zeros right there. Whoa! Where did that come? I get close to the page and it makes a mark. Let me try this again. Let me erase that ink and try it one more time. Okay. Well, it's not. Okay. That's better. Factor by grouping. Now, I'm going to group the minus sign in with it. That's not factorization right there. This will be x squared times x minus 2 plus or minus 1, right? Come on. Times
x plus 2.
X, no, you got to factor it out with minus 1. X minus 2, right? Now you can factor out an x minus 2, because that's common in both, right? And that leaves you with x squared minus 1. And you can factor that further to be x minus 2 times x minus what? 1 times x plus 1. There you got your three zeros right there. Plus 2, plus 1, and minus 1. Okay? This one. Good luck with that. Okay? You can't find this by elementary algebraic methods. So this is the one you would use Newton's method on. No reason to use it on that. You could. It should work. But you can see that. Those zeros you can find exactly, precisely, with very little effort. This one, hang that up, okay? The zeros of that function you cannot be found by elementary algebraic methods. None in the world. So use Newton's methods on that. Okay? Now, they still didn't do let's go back to this one and do the second one the third one that we did. Okay, I'm going to erase all this ink. They do this in the book, and I was trying to, goodness gracious, this thing. is slow. Let's do this for the function alpha of x is equal to x to the 1/3. Okay? Our alpha prime of x is equal to what? We already did this. What was it?
Oh, it was
1/3 x to the negative 2/3. And our alpha double prime was then going to be
negative. Negative 2 over 9.
2/9 x to the minus 5/3, right? Okay. Now, if you try to plug this in there, what do we get? Your f of x is x to the 1/3. There's dragging again. Okay. Times a minus 2/9 x to the minus 5/3 divided by this one squared, which is 1/9 x to the minus 4/3. Right? We're going to do the absolute value of all that. Well, I can see right now I can get rid of the 9. Okay? And then what we have here is 1/3 times negative 5/3 is negative 4/3. So you're going to have a negative 2 x to the negative 4/3 over a 1 times x to the negative 4/3. Okay? And these go out, and this says, and the absolute value of that is 2 and can never, ever, ever be less than 1. So no, that will never work. There is no value you can even get close to. No matter how close you get to x equals 0, unless you get right on x equals 0, then not going to work. Okay? Always going to explode. All right. Now let's go back to this one that they were talking about. X cubed minus x plus 1. What would we do? Okay. Wow. I was starting to do something with you, but this particular function has only one real 0, and by using more advanced algebraic technique, not elementary ones, you can determine, this 0 to be minus the cube root of 3 minus the square root of 23 over 3, all that divided by 6, minus the cube root of 3 plus the square root of 23 over 3 over 6. Yeah, okay, because the exact solution is written as in terms of square roots and cube roots is called a solution by radicals. And this course is not going to show you how you came up with that. Okay, I don't believe. So, yeah, maybe you can have a technique to give you an exact answer, but you have to leave it in this form because as soon as you start taking square roots of those things, you're going to have, see, this is an irrational number. This will be an irrational number of an irrational number. You're not going to get an exact solution. Same with that. When you add them, they're going to be. So that's a solution by radicals. Now you can come up with an approximation to that, but that's all you can do. Well, the method gives you an approximation to it, so why not go for it? Okay. The general formula for the zeros of a cubic function was developed much later in the 16th century by an Italian mathematician, Jerome Cardin. doesn't sound very Italian to me, published a method for finding radical solutions to cubic and quartic equations. Then for 300 years, the problem of finding a general quintic formula remained open. Finally, in the 19th century, the problem was answered independently by two young mathematicians, 300 years they had tried, and two young guys came up, Niels Henrik Abel, a Norwegian mathematician, and Évariste Galois, a French mathematician, proved that it is not possible to solve the general fifth or higher order polynomials by radicals. Of course, you can solve fifth degree equations, but Abel and Galois were able to show that no general radical solution exists. How in the world they did that at that young of an age, and then they died before they could do really much else. Pretty remarkable. Okay, enough of that. I think that's the end. Homework exercises here. Do either 3 or 5. They're both at calccheck.com, but 3 is at calcview.com. Do any of the odds 7 through 15. They're all at CalcChat. 9's at CalcView. Do either 17 or 19. They're both at CalcChat. Neither are at CalcView. Do 21. Do 23. And 21's at CalcChat, but 23 is at both CalcChat and CalcView. Sorry, I can't talk. Then do 25, it's at CalcChat. Do 29 or 31. They're both at CalcChat, neither are at CalcView. Do either 33 or 35. They're both at CalcChat, neither are at CalcView. And then there's some true-false, 37 and or 39. They should be at CalcChat. If not, just try to figure them out on your own. And then 41 is one you might want to take a look at too. It's at CalcChat as well. It should be. Okay. Sorry. I'm getting so I can hardly breathe. I don't know what the deal is. Oh, and by the way, for those of you who just came in, or came in since the beginning of class, I have a meeting I've got to go, or I'm supposed to go to, over on the Birmingham campus from 12 to 1. So shortly after we get through with this class, I'll be booking over to the Birmingham campus. And then as soon as that meeting's over with, I'll be booking it back here for my 2 o'clock class. So really my office hours almost evaporated today. I have a few minutes after class and a few minutes between the time I get back at the other class. So that's all I got for today. But they said we're supposed to be there. Okay. All right. Yes.
Do you have test 3 ready yet?
No, I'll probably have it ready on Wednesday.
I was asking because I have to leave early.
Okay. I'm sorry.
I got to do a presentation.
Oh, I see. Okay. Well, we're going to get started on they never asked me that question before. Don't say. I don't know why they asked me the question. But now they kick me completely out of the deal, so let's go back here and do 3.9. And you'll see, if you look at this, this is the last section in Chapter 3. Don't have a lot of time, but let's get started on it. And again, it's a little bit longer section, but not as time-consuming, hopefully, as the previous section was. Okay? And why is this not opening? Oh, maybe it did open. Let's see. Nope. Let's try it again. PowerPoint's doing some really strange things today. Nope. There we go. Finally. Okay, we'll open from the current slide. So we're doing applications of differentiation, chapter 3, long chapter, and we're doing differentials 3.9. Now, it says here, objectives here, understand the concept of a tangent line approximation. Okay? We've kind of hinted at that. We'll compare the value of the differential dy with the actual change in y, which is delta y. Okay? This has to do with that concept of a tangent line approximation. We'll estimate a propagated error using a differential. We'll find the differential of a function using differentiation formulas, which you'll find they really are pretty close. So let's first do tangent line approximations. Consider a function f that is differentiable at c. It's always a good place to start, okay? Make sure the function is differentiable at c. The equation for the tangent line then at the point c, f of c, is, and this sort of makes sense if you think about it. All right. Let's think about this. Here we have a point, c, f of c. We have the slope of that tangent line is going to be f prime of c, right? So, from the point slope formula, we have y minus f of c is equal to f prime of c, the slope, times x minus c. So this comes straight from the point slope formula. When that's your point and your slope is your first derivative. Okay? It looks a little bizarre, but that's exactly where it's from. Now if you add f of c to both sides, you get y then is equal to f of c plus f prime of c times x minus c. Okay? That is called the tangent line approximation or linear approximation of f at c. Okay? So what did we do there? We had a function defined at c, differentiable at c, find the value at c, find the value of the derivative at c, and the value of the derivative times x minus c, the difference of x and c, plus what x and c was. That's your approximation of what the function value is. Because c is a constant, y is a linear function, a linear function of x. Okay? Because you see, this is to the first power. These are constants. That's constant. That's constant. So y is a linear function of x. Okay? X is a variable, of course. Y is a variable. So that would be a linear function. Moreover, by restricting the values of x to those sufficiently close to c, the values of y can be used as approximations to any desired degree of accuracy of the values of the function of f. All you have to do is get x close enough to c that you can approximate y by that. In other words, as x approaches c, the limit of y is f of c. Yeah, I mean, that sort of makes sense, doesn't it? As x gets closer to c, the limit of that is f of c. We sure hope so. I mean, otherwise it wouldn't make a lot of sense, would it? Okay? So, here we have, find the tangent line approximation of f of x is equal to 1 plus sine x. Okay? At the point 0, 1. Okay? We're doing the tangent line approximation. Okay. Now, yeah, there it is. Okay. Let me write down what the tangent line approximation was again, because it's no longer on the slides. So let's write it again. Goodness, this thing is such a pain today. There's some serious problems here. Okay. All right. All right. Let me write down what. Look at that. I'm getting nowhere close to the screen, and it's writing on the screen. Okay. I don't know what its problem is today. Here's what we got. Y. And it's a different color to boot. Let me try this one more time. Nope, it's not doing it. Y is equal to, oh, there it is. It is doing it. Alpha C plus alpha prime of C times x minus C. That's your approximation. Okay? Here's your function, alpha of x equal 1 plus sine x. Okay? And so what have we got to do? Take a derivative. Alpha prime of x is equal to what? Look at that. Second? Cosine x. I don't know why these little squiggles are showing up all over the screen, but I can't help it. If I get the pen close to the screen, sometimes it makes a squiggle, sometimes it doesn't. Okay. So let's plug and chug. The point is at 0, 1. Remember, this is your x, this is your y. Okay? We want to find the tangent approximation of that function at the point 0, 1. So the y, which is what we're looking for, is f of c. What's f of, and c, remember, is your x value. F of c, but that x value is 0. Okay? Is equal to what? F of 0 is equal to? Okay, 1 plus sine of 0. What's sine of 0?
Oh, 0.
0. This is 0. So this will be what? Let's do our f prime at 0. That's our c here. And that will be what? 1 as well. Exactly. Okay. So let's now plug in. Alpha c was equal, alpha of 0 is equal to 1 plus 1 times x minus 0. Okay. So this will be 1 plus x. Right? And your x is 0. So this will be 1. Okay. Now, does it feel like you've just gone around your elbow to get to your ear? Yes, it does, because you know that it's going to be 1, okay? At x equals 0, the value is 1. But it said find the tangent line approximation of it. Now, unless there's something really squirrely that I have missed and don't see, you know, we've just done that, but it's been really horrendous way of going about doing it. So let's see what they do first. The derivative of alpha is alpha prime of x is equal to 0. Sure, I mean is equal to cosine. So the equation for the tangent line is alpha of 0 plus alpha prime of 0 times x minus 0. Yeah? Okay. And that would be y is equal to 1 plus 1 times x minus 0. So 1 plus x. And when, okay. Now, that was, okay. We weren't meant to evaluate at 0. We already knew what that was. But this function that we were dealing with, 1 plus sine x, okay, that's really close to 1 plus x, a linear function. Well, you know what? If you remember what the sine function looks like, here at 0 at 0, it's 1 at pi halves, right? And 0 at pi, Okay, and down here it's minus 1 at minus pi has. This is going to be a function that looks like this, right? Well, look at this. Doesn't that look like a straight line to you? A line of slope 1? So yeah, not too surprising. I'm sorry. That, right, remember what our formula was. 1 plus x. So, 1 plus sine x. That would then be just move everything up 1. And there's 1 plus sine x right there. Okay? You just translate up one thing, and there you have it. As long as your x is fairly close to 0. Now, if x is out here at, 3, or minus 2.5, yeah, it's going to be nowhere close to that. But as long as the x is close to 0, that is a great approximation of it. 1 plus x would be a fantastic approximation of it. And that's what we're doing, looking for the linear approximation near the value x equals 0, x equals c. Okay? And here they show that same thing. Let me see if I can get this out of the way. Notice the closer x is to 0, the better the approximation. Of course it is, okay? When you get too far from 0, it's a terrible approximation. But when you're close to 0, like negative 0.01, this is your f of x equals 1 plus sine x. This and this give you almost the same answers, okay? Almost the same answers. When you get a little further away, you're still pretty close. Those are not bad answers, okay? When you get out here, though, it's okay answers, but not great, okay? Get a little bit further, and they get really, really lousy. But anything close to that, you're not in bad shape, okay? And here's the very thing I was just saying. Here's your graph of 1 plus sine x. Sine x was down here, like I said, with the slope there. So 1 plus sine x is just going to be elevated up here by 1. And anywhere in this range here, that's a great approximation. Great approximation. Here is your approximation, the tangent line approximation. Yeah, you get out here, you're going to get further and further off. Down here, you get miserably off, okay? But in here, anything close to, as they say, inside of pi fourths, which is about 3/4, I'd say even closer to that. Pi eighths would be fantastic, really good evaluation, estimation, approximation, okay? Now, all right. All that for this, and we haven't even talked about what a differential is yet. And how much time do we have? I think maybe this is a good place to start next time. We'll start top of page 236. I doubt if we did much toward the thing. Yeah, you can do tangent line approximation, do any of the odds 5 through 9. All 3 of those are at calcchat.com. Number 7's at calcview. You could probably also do 11. It's at calcchat as well. Okay? Hold off there. We'll pick up the rest of those next time. All right. Good deal. And I'll try to have your test ready for you next time so you'll be able to work on it over the weekend. I know y'all are excited to hear that. Which means I need those first and second tests in. I'm preaching to the choir here, but I do need those in as well.